Let's look at the diagonal relationship that exists between boron and silicon. Boron silicon diagonal relation. Boron is similar to silicon in a few properties. The first one is both are non-metals. The elements below boron, aluminum, as you have seen, is a metal, and this relationship between diagonally placed elements of the second and the third periods is called a diagonal relationship, as you are aware. So both these are non-metals, and the oxides M2O3, that is B2O3, and silicon dioxide M2O3, I mean B2O3 and silicon dioxide. These oxides are acidic oxides, and the corresponding acids are boric acid and silicic acid, S3BO3 and H2SiO3, silicic acid. And another point of similarity is the hydrolysis of the chlorides, the halides. BCl3 on hydrolysis gives HOH, gives S3BO3. If you need the balance equation, of course you can easily write it. BCl3 plus 3HOH giving 3HCl plus S3BO3, and that of SiCl4. Similarly, you can show the equation 3HOH giving H2SiO3 plus 4HCl. So for balancing you have to write 4 and H2SiO3, 3HOH, okay. 4HCl, H2SiO3. Now this is another point of similarity by way of diagonal, because of the diagonal positions. Now let's think about some of the important compounds. Some of the important compounds of the elements in this group. A few of the more important of the compounds we shall think about. First of all, the halides, as I already told you, the general formula is like this. The hydrides and the halides I have briefly mentioned. Now, an acid, S3BO3, I would like to mention a little bit about that. S3BO3 is a weak acid and is a monobasic acid. I like to emphasize that. Monobasic. It would seem that there are 3 hydrogen atoms in this, but it's a monobasic acid. I would like to explain. It's not the hydrogen from S3BO3 that comes out as ionic hydrogen H+, but when it is in aqueous solution, what happens is HBOH thrice, that is S3BO3 plus HOH, because of the electron deficiency in the BOH3 molecule. Boron has only 6 electrons, as you are aware, and the OH with a pair of electrons will be attached to this, and you will have H plus released from this, BOH 4 times, H plus BOH 4 times minus. So that means this is a monobasic acid, BOH 4 times minus and H plus, and this is available in the aqueous medium, so it's a monobasic acid. And this is of some importance in the medical field. It is an antiseptic, an eye wash. It's a mild antiseptic. It is used as a eye wash also. That is one of the importances of this boric acid. Now another important compound I like to mention is borax in brief. Borax, that is Na2B4O7, 10H2O. Borax. Borax is used for several purposes, including in qualitative analysis. It is used, and also in glass industry. It is used, ceramics, glass industry. Borax. And another important compound I'd like to mention is about borazone, a special compound. Borazone. It's a compound with the structure of graphite structure. Borazone is boron nitride, Bn times. This is a very hard material. It is harder than even diamond. It is used in abrasives. Borosol, otherwise popularly known as inorganic benzene. Inorganic benzene. The formula of borosol is B3N3H6, and the structure is similar to that of benzene. Borosol, inorganic benzene, has the structure BH, NH, BH, NH, BH, NH, and from each nitrogen there will be a coordinate bond, electron pair. The lone pair electron from nitrogen will be shifted towards boron to satisfy its electron thirst, that is deficiency of electrons, nitrogen to boron. So the structure obviously is similar to the structure of benzene, and hence the name inorganic benzene. The second element of this family, namely aluminum, is worth mentioning because of its great importance, and we shall see something about the manufacture of aluminum, the extraction of aluminum briefly. Aluminum, the most important ore of aluminum is bauxite, that is Al2O3 2H2. Another ore, though less significant, is corundum, and corundum is Al2O3, the anhydrous form of this, Al2O3, corundum. There is some relevance for this form of aluminum oxide because that is the major constituent of the precious gems, emerald, ruby, etc. And the difference in the color is due to the presence of small amounts of metal oxides like, say, copper oxide, chromium oxide, cobalt oxide, selenium oxide, etc. Now, this is the major component of precious gems. And back to aluminum. Aluminum, the major oxide from which very often the element is extracted, is bauxite. We shall briefly deal with the various steps in the manufacture of aluminum. First of all, the ore is purified. The purified ore is boiled with concentrated sodium hydroxide solution, and the aluminum oxide alone will dissolve, the impurities will remain undissolved, and Al2O3 plus 2NaOH, simple equation, Cc2, balance of course, 2NaAlO2 plus H2O. NaAlO2, sodium aluminate, is soluble in water. Obviously, you can filter off the undissolved impurities. Now, this solution of sodium aluminate is now treated with more water, agitated with more water, and adding a little aluminum hydroxide precipitate. A little aluminum hydroxide precipitate is added. The process is called seeding out, to bring out the major part of the aluminum as aluminum hydroxide. You add a little aluminum hydroxide and stir it very well along with excess water. Then what happens is hydrolysis will take place, NaAlO2 plus H2O giving NaOH plus AlOH thrice. NaOH, AlOH thrice, 2H2O. So you have a aluminum hydroxide precipitated down. Aluminum hydroxide is precipitated down. And this aluminum hydroxide is filtered off and it is subjected to calcination, very strong heating. When it is very strongly heated, the aluminum hydroxide will undergo dehydration, AlOH thrice, giving Al2O3 plus 3H2O. So, calcination, strong heating in a furnace will give you pure aluminum oxide. There is another name for this aluminum oxide which you are familiar with, I hope, alumina. Alumina, just like silica for SiO2. Alumina. And this purified aluminum oxide on electrolysis will give you aluminum. But there is a problem. Aluminum oxide anhydrous, this dry aluminum oxide is a very high melting substance. The melting point is as high as around 2000 degrees Celsius. So in the electrolytic process, for you to melt aluminum oxide, you need a lot of fuel. It's a waste of fuel, and there will be some other practical problems also associated in the electrolysis. If you proceed with direct melting of aluminum oxide, there is a simple solution to that. What you do is, aluminum oxide is dissolved in molten cryolite plus calcium fluoride. Molten cryolite and calcium fluoride and fluorspar and cryolite and calcium fluoride. They will not undergo any change during the electrolysis if the conditions are appropriately arranged, and Al2O3 dissolved in cryolite, dissolved in molten in cryolite, that is Na3Lf6 cryolite. Some calcium fluoride also has calcium fluoride, and the melting point is brought down from the 2000 degrees Celsius to about as low as 900 degrees Celsius approximately, and the decomposition takes place. You have aluminum and oxygen liberated, and the arrangement, when brief, is the electrolytic cell is a rectangular vessel with an inner lining of carbon, a rectangular iron vessel with inner lining of carbon, and what you take in that cell is, as is mentioned, aluminum oxide dissolved in cryolite plus calcium fluoride, and the anodes introduced into this molten mass would be very thick blocks of carbon. A few blocks of carbon will act as an anode, and during the electrolysis, the oxygen goes to the anode, aluminum will settle down as molten aluminum in the vessel, at the bottom of the vessel, and that can be tapped out. The molten aluminum can be tapped out. As the oxygen goes to the anode, it will react with the block of carbon to form carbon dioxide. That's why you take thick blocks of carbon, and when the carbon blocks making up the anode becomes thin, very thin, you replace that. That's the approximate arrangement for the manufacture of aluminum. And aluminum, the practical importance, the industrial importance is well known to you, and it's an excellent conductor of electricity. Unlike boron, boron is a non-conductor, aluminum is an excellent conductor of electricity, and there several alloys of aluminum are of great importance. And just a few of them I will mention. Magnesium, alloys of magnesium. A few important alloys of magnesium are magnesium. As the name indicates, the components are magnesium plus aluminum. And duralumin, light, at the same time very strong. Duralumin. So in the aircraft industry also it's desirable. Duralumin. Duralumin, the above, magnesium plus aluminum plus manganese and copper. Magnesium plus aluminum plus manganese and copper. And another one is alnico. Alnico. As the name indicates, it contains aluminum, nickel and cobalt along with alnico. Cobalt along with steel plus steel. This contains steel containing these aluminum, nickel and cobalt. That is alnico. I would like to mention at least one more. That's rolled gold. A favorite item in ornamentary, low cost ornaments, rolled gold. That's copper plus aluminum. Aluminum and copper. Small amounts of aluminum, copper. Copper plus aluminum. And these are the major, some of the more important alloys of aluminum.